So Taylor polynomials, what is our idea? The main idea is if we're given a function, specifically a differentiable function, we often say smooth, so I can take infinity derivatives of some function, let's call it f of x. We want a polynomial approximation to f at some point. We'll call it x equals a. We did this in Calc 1. We did degree 1 polynomials, our linear polynomials, linear approximations. All those are essentially the same thing, where we would have some function, and then at some point a, well, what do I want? Maybe the function is hard to compute, right? Like natural logs or any trig functions. The actual values are hard to compute, so what we want to do instead is we'll pick some nice value that we can compute of the function, which is usually our a, our starting point, and we can come up with a tangent line. And the line touches at that point, and then let's say I want to know, well, what is the value of this function f of x at some point close to a? Let's just call it a plus h, let's say. Well, I can't actually compute this value because the function we originally had was natural log or something. And as soon as I know natural log of 1, that's 0, but natural log of 1.5, what's that? We can't actually compute it. But 1.5, well, it's not too bad of a number. We could maybe plug it into the tangent line, and we're going to be a little bit off from the actual value of the function, but it's a close enough approximation for whatever purposes we have. This is actually how calculators work, except instead what calculators do, let's say I want to compute sine of some value, something like sine of 2 radians. What the calculator actually does is say, well, how does a calculator or a computer understand sine? It actually picks a polynomial. So, well, this value is close, the line is close, but if we want to approximate it, say, using a degree 2 polynomial, well, now we're going to be a little bit closer because we have this parabola that we can have that now passes through that point. And, well, maybe because I have this extra degree, this degree 2 polynomial, now not only am I close to the function at the point, but we're remaining closer to the function for a wider width, right? After a certain width that we get away from our base value from this fixed a point, the line diverges quite a bit. It gets further away and is not a good approximation to the function. But you can kind of see that, well, the polynomial, a degree 2, it kind of, well, encodes a little bit of the curvature of this function. So it's going to be a better approximation. And so the question is, well, what is the process? Let's say I want to take a higher and higher degree polynomial. How would we go about finding the polynomial? Okay, well, what do we want out of the polynomial? Let's pick our polynomial. I'm going to call it p of x. And we want it to be centered at a given point a. And so what I mean by that is, well, polynomial, let's start with our lowest degree constant at C0, and then we'll have some linear term. And instead of C1 times x to the 1, I'll have it C1 times x minus a to the 1 plus C2 x minus a squared. And I'm going to keep going up to however many degrees we want. In this case, let's say I want n degrees out of this polynomial. And so immediately we can kind of see, well, what's the nice thing about using this x minus a? It's still just a generic polynomial because I can adjust the constants however I need it. But by setting up the polynomial in such a way, we can actually solve for the constants much more easily. So of course, the first thing we want is that at this special value, I want my polynomial to match the value of the function. I need, right, I can compute this. Maybe it's sine of pi over 2. And I know a is pi over 2, and I can at least compute that. But if I want to know now sine of 2, well, pi over 2 is kind of close to 2. Pi over 2 is what? Like it's 3.14 divided by 2. So it's maybe like, 1.55, 1.6-ish is what pi over 2 is approximately numerically. So sine of 2 might be close to that. And maybe I can use an approximating polynomial for that. But at least I know the value of a function at one special point, and I want my polynomial to match that. And so what does this tell? This condition is going to give us information about, well, what do these constants need to satisfy? And of course, well, what is P of A? If I plug in A here, all of these higher terms, degree 1 and beyond, are going to be 0. So P of A is just the initial constant there, our constant term. Which means that this C0 is easy to find. It's just the value of the function at our special point. Good. We're good on that. We can compute that one value. That's at least our starting point. Well, what else do we want out of this function? With a straight line, what did we do? Well, we found that point and started there, but then I wanted a slope. And what was special about the slope? It's the tangent line, right? The slope is the same slope of the function at that point. So the other thing we want is that the derivatives of the function at this point A should match. Okay, well, let's compute this. So f prime of A, still a generic function. We don't know much about it. But again, if I can compute f of A, we assume that we can probably compute the derivatives of this function at that point. And p prime of A, well, by our generic polynomial, what is p prime of A? P prime of x, the constant term goes away. And then nice enough, because we only shifted over by a constant, the chain rule from these terms, from the higher power terms, isn't going to add anything else. So p prime of x is going to be c1 times this term to the 0 now, so that goes away, plus 2c2 x minus a to the 1 plus 3c3 x minus a cubed. And it's going to go all the way up to our nth coefficient, but because we took a derivative, the power is 1 less. And so again, what happens when we plug in A? All of these higher order terms, did I skip a term? X to the 1, x to the, sorry, this one should have been 2. Because we dropped that 3 down and reduced that to degree 2. When I plug in A, all the higher order terms drop out, and we just get our first constant. or our degree 1 constant. So in other words, this condition that we want, that the derivatives should match, tells us how to find this other constant to model this polynomial for our function. So this C1 should equal f prime of a. So let's box these or put them somewhere. So our P prime, our C1 is f prime of a, our C0 is f of a. Let's do one more, because those first two can be a little misleading. What we're trying to do ultimately is I want to find a general formula for these CNs. If I can find, of course, because n is arbitrary, I want a general formula in terms of, well, what is my nth coefficient going to be, or what is my kth coefficient going to be, and can I compute that in terms of the value of the function and its derivatives? Well, we kind of see a little bit of a pattern. Of course, C0 corresponds to the value of the function. C1 corresponds to the first derivative. What should our C2 be? So again, what else do we want? We want to take this a little bit further, because we don't want just an approximating line. We want maybe an approximating parabola or approximating cubic. So not only do the values of the function, the first derivative, have to match, but let's try to get closer and have the second derivatives. So we want the second derivative of our polynomial at this special point to match the second derivative of the function. And so from our previous computation, here is our p prime of x. So what does this statement say? If this is what we want, what can we deduce? Our second derivative of our polynomial, again, the constant terms are going to go away, and we will have 2c2. That will be degree 1. We will have 3 times 2 c3. That will come down to a degree 1 term. And we're going to keep taking derivatives of all the successive terms. And our last term, we will have an n times an n minus 1. We will have our nth constant. And then, of course, we will lower the degree of this last term. Will be down to n minus 2. And so our p double prime of a is just 2c2. Okay, well, a little bit different pattern than what the previous two were, because I have this 2 there, but it's still just a constant, not too big of a deal. And by this condition, I want 2c2 equal to f double prime of a. In other words, our c2 is going to be f double prime of a over 2. So now we see the pattern's not as clear now. And maybe we'll do one more. So let's take a look at see what's going on with the pattern of these coefficients. My C2 term has to relate to the second derivative. But now I have these extra constants that are going to be coming out. So we just have to keep track of those and see what's going to happen with these constants. Well, these constants are coming out because I'm taking successive derivatives. And every time I take a derivative of a polynomial, we follow our power rule, of course. It's going to be the power times the multiplied out front, and then lower the power. And so every time I'm taking a derivative, I'm getting another constant multiplied in front of that term. Well, what's happening with these constants? I took, my degree 3 term, I took one derivative, gave me that 3. The second derivative we just did gave us that 2. So I got 3 times 2. What should this fourth term be here? Let's rewrite this and include one extra term. What's this pattern doing? So the degree 4 term, or the term that was originally degree 4, I would take one derivative and I would have that 4. Now it's a degree 3 term. And then on my second derivative, I would have that 3 come down. And it's a now degree 2 term. And so if I take a third derivative, constant term drops out. I will get 3 times 2 times C3. And now all the other constants now have another term, another constant being multiplied that is 1 less than the previous one, right? These keep incrementing down by 1. And then, of course, the power of that part of the polynomial decreases as well. And so our last one will be n times n minus 1 times n minus 2. And degree, sorry for trying to squeeze that in. Degree n minus 3 on that last term. But what is the other pattern we're seeing? I don't just want this polynomial, the third derivative of this polynomial. We need the third derivative evaluated at a given point, because I need this to match the third derivative of the original function at that point. Again, this is what we want. And what's it tell us? Well, what's happening every time I plug in this a? We only get this constant term here, right? This happened in the previous one. I compute my second derivative, and anytime there's an x minus a, degree 1, degree 2, all the way up to whatever degree our top degree is remaining, I plug in a, and all those terms go to 0. And this is big purpose, or the main purpose of this x minus a. It makes all those terms go to 0, and it sort of dictates that this degree 2 term, and only this degree 2 coefficient, is needed to determine the second derivative, or it encodes essentially the information of that second derivative of our function. And just like here in our next one, this tells us that our 3 times 2 times C3 is going to equal f triple prime of a. So in other words, C3 is f triple prime of a over 3 times 2 now. And I'm intentionally not multiplying those out. So we've done 4 terms. Let's make a guess. Because for a general formula, for any term, I want some formula for the kth constant, right? I'm still trying to construct my original polynomial, and using the information about these derivatives, we're finding what the values of these constants need to be based on that function. And we found the first 4, but of course, this could be a 10th degree polynomial. I don't want to go through every single one individually. I would like to have at least some sort of formula for this. And this is the type of formula that a calculator can easily compute and check and plug in and do quickly with some sort of like iterative loop. So what should our kth constant be? Whatever k is, 0, 1, 2, 3, all the way up to n. Well, let's look at what we got. Let's see if I can put that all on screen. One thing that's pretty clear is that whatever degree constant we have only depends on that degree of the derivative. Third constant, third derivative. Second constant, second derivative. So we know that the kth derivative is going to be involved. So we take k derivatives of the function and evaluate it at our special point. But we're also seeing some constants in the bottom. And what is happening with those constants? Can anyone kind of guess? So what's going to happen? Like, what's the next constant going to be? Where did this 3 times 2 come from? Came from the fact that our C3 came from our original third degree term. When I took one derivative, that brought out the 3. I take a second derivative, that brought out the 2. And it's not until I take the third derivative that I just got this constant term, and then I could solve for it. So in other words, it's not until I essentially take all of the derivatives needed, in this case, k derivatives, that we will sort of multiply by all of those constants. We will multiply by k minus 1, k minus 2, and those will keep coming down until there's no more constants, until it's just 1, and that kth term becomes a constant. And so what is our mathematical tool now that we have to model this type of phenomenon when I'm multiplying by successive integers, successively decreasing integers, right? Because really there's like a hidden 1 here, and there's a hidden 1 here. And there was hidden 1s in the denominators of those first 2 as well.
Factorial.
Factorial, yes. So this is our formula. For our kth terms. And now it's pretty, at least straightforward. Let's do one example with this. So let's suppose we have a function. This is going to be related a bit to the homework on homework 8, number 5. I think I'm actually going to go over it tomorrow. It's a tricky problem, but it has to do, at least in relation to a function, let's say f of x is, natural log of 1 plus x. And our goal is to find, let's say, a degree 3 polynomial. To approximate f of x at, we need to pick a point. What's our special point? We have to pick a point that I can compute. And if it's 1 plus x, I can compute natural log of 1, right? So we nice enough sort of have that function shifted in such a way that I can just pick x equals 0. If you see the word like Maclaurin series, this is all they mean. When you see the word Taylor series, it's essentially this polynomial we started. General polynomial is a Taylor polynomial. If they say Maclaurin polynomial, it just means a is equal to 0. We're just centering it at 0. So don't get thrown off by that. It's essentially, it's all the same process. Okay, so by our formula, we have our polynomial of x is going to be c0 plus c1 x, since our a is 0, plus c2 x squared plus c3 x cubed. And so what do we know? We know that our constants now are related to the kth derivative evaluated at 0 divided by k factorial. This is our formula for the constants. And so how do we go about doing the process with this? It helps to find a generic formula for the kth derivative of f of x. In this specific case, it's not going to be terribly important for this step because we could just compute 4 of them. But there might be questions that say, find a formula for the kth coefficient of the Taylor polynomial. And in the next coming days, of course, we're going to be taking infinite degree polynomials. And so I want to come up with a generic formula for this that's a little more nicer and not just written as f to the, the kth derivative of f. I want the actual expression for the kth derivative of f. So you do that essentially just by computing. So, of course, f of x is natural log of 1 plus x. And I'm going to make it in sort of a table. So generic as the function, and then evaluate it at x equals 0. So our f of 0 is 0. Our f prime is 1 over 1 plus x. F prime evaluated at our special point is 1. F double prime of x is, so this is 1 plus x to the minus 1, so we will get minus 1 plus x to the minus 2. F double prime of 0 is negative 1. So I would recommend doing at least 3. Let's do one more. So of course, with this specific problem, this is essentially all we would have to do. We could just, do our 4 terms and stop. What's going to happen with this guy again? Now this is 1 plus x to the minus 2. So it will have a minus 1 times minus 2 times 1 plus x to the minus 3. And f triple prime of 0. I plug in 0 then, and what do we get? Just 2. So just for the sake of practicing this, you would want to then maybe make a note of just, making some dots and then come up with a formula for your kth derivative of x. And what's going to happen? So my 0th derivative is something like natural log. Well, this one's kind of the odd one out of the pattern. But at least my first derivative is 1 over 1 plus x. Second derivative, 1 over 1 plus x squared. Third derivative, different constant over 1 plus x to the minus 3. Sorry, that 3 should be positive. So I know that the kth derivative should have this 1 plus x to the k. And then what are the constants doing? Well, my first derivative is positive. Second derivative is negative. Third derivative, back to positive. Because I'm multiplying by these successive negative exponents every time I take a derivative, we should have something like a minus 1 to the k. That'll give us an alternating sequence. But we do want to check the index. So when k is 1, we should be positive. Well, that's not right. And when k is 2, it should be negative. So that's going to give us an even. So we're off by 1 index. So you can either just add 1 or subtract 1. Will give us that formula, or at least that part of the formula. And then what are the constants doing? So f triple prime, I have 2 times 1. The next derivative, the 4th derivative, would have that 3. 3 times 2 times 1. So it looks like I'm taking one number less than the number of derivatives. So my third derivative, I have 2 times 1. Fourth derivative, 3 times 2 times 1. So however many derivatives I take the number 1 less than that, and then multiply all of the numbers less than that. So we got our factorial there. So this is our general formula for the kth derivative. And for our general constants, if we wanted to compute higher order terms, I plug in 0 now to this guy. And so what do we get? We get our minus 1. X is 0, so we'll still have our k plus 1. And then, of course, 1 to the k is 1. And then we get k minus 1 factorial. And so this is our C0, C1, C2, C3. And then this guy is our general expression for CK. We'll get to more of this in the next coming days. I just wanted to kind of see that and get you guys kind of thinking about the pattern recognition of computing the first few ones. So for the sake of this problem, though, the bulk of our work was with these first derivatives. Because I only wanted a degree 3 term, I only needed to go up to degree 3 and compute my constants. Oops, sorry, so this isn't quite C1. This is C0, C1, and of course, I've got to divide these by our k factorial. So the derivative is the constant times that factorial. Solving for my constants now, I would just divide by those factorials. So our polynomial, our p of x, is, well, our first constant is 0, plus our c1 is 1 times x, plus our c2 is the second derivative evaluated at 0 divided by 2 factorial. So 1 over 2 factorial, negative 1 over 2 factorial, x squared, plus our last term is going to be 2 divided by 3 factorial, x cubed. Sorry, that's off the screen. And so simplifying those guys, our polynomial is just going to be x minus 1/2 x squared plus, so 2 over 3 factorial. 3 factorial is 3 times 2 times 1, so the 2's will cancel, just 1/3 x cubed. And this polynomial is close to the function natural log of 1 plus x. Any questions on that? Here, maybe we can compare. Can you guys see that? I don't know if that's coming up. Doesn't look like you can see it very well. Let's see if we can maybe do some computations. Here, so let's put these functions in. So we've got natural log of 1 plus x is our y1. What was our polynomial? It was x minus 1/2, so I'll just type it in as 0.5 x squared plus 1/3 x to the third. So that was our degree 3 polynomial. Let's compare it with just the degree 1 polynomial. The linear approximation to that is just the first term, or the constant term plus the degree 1 term. The constant term is 0. So if we were to try to find a linear approximation to this function 1 plus x, it would essentially just look like x, y equals x. And let's see, minus 1 to 4. Let's see if we can graph that. Can you guys see that, or is the light messed up? So you can kind of see, so the natural log was this first one, and you can kind of see how, can't tell if that light helps, maybe if I keep it off center. The natural log, you can see the straight line getting above the cubic. And even though the cubic gets, way away from the natural log as the x's get bigger, it's actually really tight for a much broader region. And we can check that with our table as well. So we've got x equals 0. We've got x equals, let's say, 0.2, 0.4, 0.6, 0.8, and 1. And so our, I didn't say it. So our y1 was our original function. And you can see our y2 was our approximating polynomial. See how close those numbers are? And even up at 0.4, they're still pretty close. And you can kind of see that our approximating polynomial in the second column, this was our linear polynomial. These numbers start to get a little further away from the original value. So that's all the basics of Taylor polynomials. Any questions on any of that? Questions on the computations, the formula? I can keep the formula up here. Okay, so let's go ahead and put ourselves into groups and spend the rest of the time doing the activity. So the activity for today, if you go to the schedule on the website and click on the introduction to Taylor polynomials, it's a pretty good activity. We want to do the same process, except the function we're going to work with is e to the x. And e to the x we'll find has very nice derivatives, and it'll have a very nice formula for all the successive derivatives that we can find an approximating polynomial for.